Good morning, everyone. We are very excited today because we have a very good webinar coming up for today's, the third Direfuse webinar. Um, Today, we are going to have Argonne National Lab, but before we go into the details of that, just a reminder of the Disaster Resilient Food, Energy, Water Systems program. It's a convergence research initiative that's sponsored by the U.S. National Science Foundation on Sustainable Regional Systems Research Network. And our partners in this span over the geographical regions of Texas, Louisiana, and Mississippi. And also we have national and international partners that are participating with us. Today's webinar is being given by Argonne National Lab, who is a core partner in this initiative, who is helping us during the planning phase, and will be giving a very nice overview of the work at Argonne National Lab's Systems Assessment Center. So we have upcoming webinars under Direfuse. In May, we are having role of industrial symbiosis modeling for sustainable regional systems. It is going to be given by myself and my colleague, Professor Mahmoud El-Hawagi from Teas Gas and Fuels Research Center. In June, we have a webinar coming from the American Bureau of Shipping group, which will be on private sector projects for disaster-related water systems management in local, state, and federal government. We also have webinars upcoming in the following months, and very soon we are going to update our website. So if you go to our website and subscribe to our webinars, we will be able to give you that information in your inbox. Our registration for our workshops are also open now. The Mississippi workshop is in May, and the Louisiana workshop is in June. So if you are from any of those regions or know somebody in those regions who may be interested to participate in the workshops, please let them know. We want to have a diversity of different participants. So please spread the word, and we'll be happy to take in registrations for those two workshops. The registration for our Texas workshop is going to be open soon. We are finalizing on the final panelists, and that is what we will be doing over the next few days, and we'll be able to get you the final panelists for that workshop. So we have the workshops page set up under the Direfuse website. Please navigate to the workshops page to see who the panelists are and what the format is. And if you're interested, please register for the workshops. The workshops are in person, and so that's why we want to have the in-person registrations for these workshops. The workshops are going under the same format, but 3 different locations. Texas, Mississippi, and Louisiana. The highlights are we're going to have an opening plenary panel of very high-level speakers. You can go to our website to see the speakers for Louisiana and Mississippi. And we are terming it an anatomy of a disaster, so that we are able to get different perspectives from the society on these disasters that we face. We will be introducing the Direfuse Consortium Development Initiative after this. And then we'll have an intense breakout session on convergence research. What are the different topic areas under convergence research that we intend to achieve through Direfuse? And then we have 2 parallel breakout sessions on diversity, equity, and culture of inclusion, and education and workforce development in this area. And finally, we will have 2 tutorial sessions. The tutorial sessions are in parallel. Rapid Institute, our partner, is going to give a tutorial on modular process intensification. And we are also going to have a combined tutorial session on water energy food nexus and methods to facilitate systems analysis under that umbrella. So these are very nice 1.5-hour tutorial sessions to get you introduced to some of the recent topics that are related to our Direfuse program. We have our website, so you can visit us at our website. It is searchable in Google. So if you just search with Direfuse, it should be coming up. We also have a subscription page. So if you want to receive updates, express participation interest, and if you want information on future events, please subscribe to our subscription page. With that, we have the introduction for today's webinar. So today's webinar is going to be given by Argonne National Lab, and specifically Troy Hawkins. Dr. Troy Hawkins is from the Systems Assessment Center. And with him, we have two of his colleagues, Jared Kelly and Yusing Lee. And we are going to learn about the life cycle assessment and analysis methods, as well as focus on two case studies on battery electric vehicles and electricity resilience, and guiding the takeoff of sustainable aviation fuels. With that, I'll stop sharing and over to you, Troy.
Great, thanks, Devalina. Can you see the video okay and hear me all right?
Yes, we can see you, and we also see your screen.
Okay, and the screen that you see is the full screen slides?
Yes.
Great. Great, well, it's my pleasure to be here today. And I'm really glad to be part of this NSF Convergence Research Initiative. I'm glad to be representing some of the research that we do at Argonne National Lab. So let's jump into it. Just as a brief introduction, there will be three of us speaking here today. Myself, I lead the Fuels and Products Group within the Systems Assessment Center at Argonne National Lab. And I'll be giving kind of an overview of the tools that we use for life cycle analysis and some of the type of work that we do. And then Jared Kelly and Wisung Lee will be giving deeper dives into work that we do on battery electric vehicles and sustainable aviation fuels. I apologize, I think my slides aren't changing correctly. Okay. Go. So starting with just a quick overview of Argonne National Laboratory. We're a national lab, part of the U.S. Department of Energy Office of Science, and we're located just outside of Chicago in Lamont, Illinois. The lab was grown out of the nuclear research program. Basically, that was moved from the University of Chicago when it was decided that it would be safer to have it outside of the city. The lab has been operated by the University of Chicago since its inception. We're now about 1,700 science and technology staff, over 300 postdoctoral researchers, and then a number of visitors and faculty that are joint with the lab. Many users come on site to use the lab's facilities, in particular the advanced photon source and some of the other unique capabilities. The lab employs over 3,500 people, and we have about over 500 students on site. And I'll just say that the work that we do is one small piece, obviously, of what the lab does. but Argonne for, gosh, over 30 years has had a very advanced analysis program on transportation technologies, sustainability, and actually across a range of different technologies. So then just a brief introduction to the Systems Assessment Center that we're all part of. The Systems Assessment Center consists of about three groups and about 50 to 60 staff members within those groups. And our goal is to provide insights and tools for research and development and policy decisions. Lifecycle analysis is one big part of what our group has been doing for many years. But we also work on a range of systems analysis techniques, approaches, including techno-economic analysis, scale-up analysis, diversity or equity and inclusion analysis, environmental justice and energy justice aspects. And as I said, what we'll focus on in this presentation is primarily life cycle analysis, but I'd be glad to follow up with anybody who is interested in any of the other capabilities. So now I'd like to introduce the GREET tool that is one of the flagship models within our group. GREET stands for Greenhouse Gases, Regulated Emissions, and Energy Use in Technologies. It's used to track the life cycle performance of energy systems and products, and it's funded by the U.S. Department of Energy for many years and used to inform and guide Department of Energy research. We've been developing GREET since 1995, and it's had annual updates and expansions. We're regularly looking at the data to keep those up to date with current technologies and future projections. We've had long-term support from the Vehicle Technologies Office, the Hydrogen Fuel Cell Technologies Office, and the Bioenergy Technologies Office. And in more recent years, GREET has expanded. It was originally focused on transportation and now includes a wide range of technologies, including fuels, vehicles, chemicals, plastics, agriculture, metals, concrete, and industry more generally, buildings, batteries, electricity infrastructure. And here I'd just like to say a few words about life cycle analysis and the scope of the GREET tool. The goal of life cycle analysis is to understand all of the environmental aspects of a system from generally think of materials from cradle to end of life. So if you think of a vehicle, it's any of the materials that get extracted to produce that vehicle, anything that's recycled and components put into that vehicle, manufacturing of the vehicle, use of the vehicle, and then the eventual end of life, which involves some recycling and some disposal. GREET is broken out into two parts. GREET 1 focuses traditionally on the fuel cycle of transportation systems, whereas GREET 2 focuses on the vehicle cycle. These address all of the major life cycle stages. We have a number of deep dive modeling efforts to look at feedstocks for fuels such as petroleum, natural gas, and biomass and other resources, conversion of those to various fuels and energy products, and then the use of those. In the area of biofuels, we've had a lot of efforts on looking at direct and induced land use change, which is an important part of those impacts. Oops, I'm sorry. And then, well, GREET has historically been US technology centric. We now have separate models to represent China and Middle East, North Africa. And for sustainable aviation fuels, now looking at broader international coverage. GREET also is distinct in that it includes time series projections, and it allows for uncertainty analysis using Monte Carlo analysis. The scope of GREET includes all of the major transportation subsectors. Here you can see road, rail, air, and marine. The percentages are the contributions to the total US greenhouse gas emissions from each of these sectors. So you can see while there's some major differences, all of them are significant in the scope of US transportation emissions. And I'll also say, I believe in all of these sectors, we're active looking at both fuel technologies as well as fuel cells and battery electric technologies. This slide focuses on the metrics that are tracked in GREET. So we have four main areas: greenhouse gases, criteria air pollutants, energy use, and water consumption. And within each of those, you can see the individual flows that are tracked. I think many people will be familiar with these. We characterize greenhouse gas emissions using global warming potential, which is established by the International Panel for Climate Change in their AR5 report. For criteria air pollutant emissions, the exposure matters, and so we track and distinguish between urban and non-urban emissions. And when it comes to water consumption, I'll talk toward the end of my section about a model that we have for water stress called AWARE-US, which helps to estimate the differential impacts of water depending on where it's used. Now, just a few words about the impact of GREET. GREET has a large, global, and diverse user base. You can see on the upper left here the registered users, and at this point we have over 50,000 registered users of GREET. And as you can see, this continues to increase. The distribution of those users, we have globally, most of those are in North America, but significant numbers of users in Asia, Europe, and then other regions, which you can see there. And then you can see we have about half of our users are from academia and education, and the other half of users are from across industry, research institutions, government agencies, private consulting, and nonprofit groups. And then the logos here show kind of a group of various sponsors and users of the GREET model. This isn't fully inclusive, but just to give a flavor of some of the different organizations that are involved in our work. And one of the things that we take a lot of pride in is that GREET is used to inform policies and regulation. One of the most significant uses of GREET is California GREET, which is an adaptation of Argonne's GREET model by the state of California for use in its low carbon fuels standard for the evaluation of the carbon intensity of fuels evaluated under that standard. Other states also have similar programs, Oregon and Washington, and they also use adaptations of Argonne's GREET model for their evaluations, following what California does. The U.S. Environmental Protection Agency uses GREET together with other sources for its renewable fuel standard pathway evaluations. We recently contributed to the biofuels report to Congress through the EPA. The National Highway Traffic Safety Administration is using GREET for fuel economy regulation. You'll hear more later in the presentation about our use of GREET to support the Federal Aviation Administration and the International Civil Aviation Organization to evaluate aviation fuel pathways. GREET was used to produce the Well to Wheels report for the U.S. Drive initiative. It's being used by the U.S. Maritime Administration, first for looking at low sulfur alternatives, biofuels as low sulfur alternatives, now focusing more on IMO greenhouse gas intensity regulations and inland vessels. The U.S. Department of Agriculture is using GREET for bioenergy LCA, and the Canadian Clean Fuel Standard through the Environment and Climate Change Canada is also looking at fuel pathways similar to what California is doing. So in this next section of the presentation, I'll just give a quick overview of 3 areas that we're working in to give you a sense of some of the breadth of the work that we do with GREET and some of our recent accomplishments. The intent isn't to give all the details. You can find our publications on our website and read more about these. So the first one is the Co-Optimization of Fuels and Engines Consortium. We're a member of this consortium together with a number of other Department of Energy laboratories and external partners located all across the country. The goal of the consortium is to identify cost-effective, low-carbon biofuels for diesel engines and to quantify their potential costs and benefits at scale. And so the slogan for this is better fuels, better engines, sooner. And within the consortium, Argonne leads the analysis team, and the analysis team is looking at costs and benefits across scales. So one of the things we're doing is to look at the cost, greenhouse gas emissions, and other environmental effects of biofuels. We've done this for light-duty vehicles and then heavy-duty vehicles. Here in the presentation today, I'll focus on our work on heavy-duty vehicles. We've looked at the value that diesel-like biofuels could provide the refining industry by analyzing, integrating bio blend stocks into refinery operations, and doing that both from an economic and environmental perspective. We've looked at consumer preferences and choice of purchasing co-optimized engines and biofuels using adoption modeling and scale-up modeling. So we've used a series of different models at the National Renewable Energy Lab and Argonne for that work. And then ultimately looking at the economy-wide benefits in terms of environmental benefits, economic benefits, job benefits of biofuels at scale. So here's one of our outputs from the life cycle analysis and techno-economic analysis portion of the work. Here it was Argonne primarily doing the life cycle analysis, and the National Renewable Energy Lab and the Pacific Northwest National Lab doing the techno-economic analysis. On the screen you can see the figure on the left is the life cycle greenhouse gas emissions for the fuels that we analyzed, and the figure on the right is the minimum fuel selling price, or the result of the techno-economic analysis. You can see the list of bioblend stocks on the left, and you can see we analyzed a large number of different molecules that could be used as fuel additives. These are meant to be performance enhancing. They should reduce the NOx and PM emissions from heavy-duty vehicles, which is a major concern for meeting future more stringent emissions regulations. These were screening level assessments, and that's the reason why we've left the numeric results off for the minimum fuel selling price, rather to show a range. But here you can see the contributions to each of these. But what we see is that, well, I'll say many of the experimental researchers going into this program had the perception that any biofuel would be low greenhouse gas emissions. And it turns out that's not necessarily the case. And there was a lot of interaction between members of the research team to down select the key fuels. But this is shown in these results that show a wide range of greenhouse gas emissions across these fuels. And a key challenge is reducing the cost. You can see even for the, across the whole range, we have a range of costs. But generally, good news is that the lower greenhouse gas emission fuels, some of them tend to be the lower cost options as well. We took this one step further to look across a series of metrics spanning technology readiness, economic viability, and environmental aspects so that we could screen these fuels. So Here, I won't go into a lot of detail, and I apologize that this is a bit of an eye chart, but the green dots reflect more favorable outcomes for the fuels in those categories. The blue are neutral, the orange are unfavorable, and then the gray are where we didn't have enough data to make a determination. You can see that some of the columns tend to be more green. In some cases, that's the result of the ways that we use to select the fuels. So by definition, we're selecting more fuels that have less co-product dependency, market competition, and a lower feedstock cost. All right, next here I'm going to move into another area of our work. This project is one that we have with 4 national labs, Argonne, Oak Ridge National Lab, Pacific Northwest National Lab, and the National Renewable Energy Lab. And this is looking at opportunities for biofuels for maritime shipping. The objective of this work is to accelerate the uptake of biofuels for marine shipping with analysis and testing, and to lay the groundwork for biofuel demonstration. Our role in the project, again, is analysis, and I'll show you some of the life cycle analysis results that we have. Here again, we've screened a series of fuels. There's actually 2 parts to this project. In one part, we're looking at bio-oils or minimally processed biofuels, which is kind of a newer category of biofuels that DOE hasn't looked as closely at. The idea is that you can have a lower cost to be more competitive with the heavy fuel oil that's typically used for as a shipping fuel. Heavy fuel oil is almost a waste product of the refining process. It's very thick and viscous. It's closely related to asphalt, what's used to make roads. In fact, it's so viscous that it needs to be heated in order to flow into the engine. And so you can imagine that it's difficult for a highly processed, high quality biofuel to compete with that. So we're looking at using hydrothermal liquefaction and pyrolysis and catalytic fast pyrolysis to produce low cost, low carbon biofuels for that purpose. In the other part of the project, we're supporting DOE's mission innovation, low carbon or net zero fuels for shipping initiative. And there we're looking across a wider spread of fuels and further into the future, things like ammonia, methanol, and e-fuels. So on the screen here, you can see on the left the list of fuels that we've evaluated. Again, you can see the contributions to the life cycle greenhouse gas emissions on the right. These are broken down into the life cycle stages. And an interesting thing here is that a number of these pathways can achieve a net negative greenhouse gas emissions. This is because they displace emissions that would occur as a result of business as usual management of the waste feedstocks that are used. These ones are produced from manure, landfill gas, and wastewater sludge. So those all emit methane when they're disposed, and the use of them to produce marine fuels eliminates or reduces those methane emissions, and as such, then you can end up with a net negative carbon intensity. But all of these fuels, well, the fuels that are on the lower end of the spectrum are biofuels, some e-fuels, which we've modeled using low carbon electricity, which is something we anticipate that the grid will be decarbonizing in future years. And then on the higher end of the spectrum, we have fuels produced from fossil resources. A caveat here is we haven't, there's ideas to use carbon capture, but the challenge with the fossil fuels is that the carbon that's emitted is contributing to global warming potential. One more slide here on marine fuel pathways. So this slide, we've looked at the greenhouse gas emissions and the minimum fuel selling price together. And just to, in the interest of time, I'll go real quickly. The different colors here represent different pathways for producing these fuels. And we can see that the black is the fossil pathways, and the lower end of the cost for the black dots are, we can see low sulfur fuel oil, LSFO. So that's kind of the benchmark. So that's at 1 and 1 for these ratios. And so anything below that, all of the fuels are below that, they have lower greenhouse gas emissions. And then anything, or to the left of that, I should say. And then anything lower than that has a lower price. So we do see HTL of manure and sludge potentially could have a lower price. And then we see other biofuels and waste-based fuels that could have lower greenhouse gas emissions with an additional cost. And the feedstocks that are used to produce these fuels are limited, so multiple pathways would be needed to meet the total demand. And as these things scale up and we gain industry experience, we expect that production can become more optimized and these prices would then fall. The last area I'm going to talk about here is our AWARE US model. And this is addressing the question, how can we maintain water sustainability while scaling up energy production? So we used a method that was actually first developed elsewhere and adapted it for our purposes in the US by developing characterization factors for county level water impact analysis. We started this work by developing county level factors, and then you can see the map changing here. We realized that throughout the year, the water stress would change. So we developed those on a monthly basis and then use those to analyze different systems. The one I'll talk about today is algae. So I'll go to the next slide here. We're using AWARE US to guide development of algal biofuel systems. And this, this grew out of our analysis of water consumption. And we realized that wasn't sufficient because of these regional differences in water stress. So you can see here, this was looking at where would be suitable locations for siting algal biofuel systems. And some of the background is that, the southern US is more suitable. It has more sun and warmer weather. You don't lose productivity in the winter months as much as you would further north. But you have some regions with extreme water stress. And so you can see the color coding there. The red counties are those with much higher water stress. And there's a number of those in Arizona and Texas, New Mexico, which could otherwise be very suitable locations for algae production. But because of the high evaporation of water from algae ponds, those could end up causing significant water stress. What's being done about that is DOE is working on technologies for growing algal biofuels using non-potable and saline water so that it's not competing with freshwater sources. That presents challenges of its own, and that's the topic of continued research. The last slide here. Actually, there's one more thing I want to say on this slide. And part of the reason I wanted to show this one is that the region, the focus region for Dyer Fuse turns out to be quite a beneficial region for growing microalgae because of some of the things that I just said. But some that may not be obvious, rainfall is important, so that can replenish the water in the ponds. The sunny days and warm weather, that contributes to the yield of the algae in the ponds. And let me go to the next slide. The last thing I'll talk about here. Algae ponds require a CO2 source, and the system that we're looking at has an industrial CO2 source. So that could be something like coal power, but it could also be high purity CO2 sources, such as those from steam methane reforming, ammonia production, or ethanol production, which produce CO2 at a very high concentration, which can be compressed and delivered to the pond almost directly without cleanup and at a much lower cost. So here we looked at algae production in different states, focusing on the differences in high purity CO2 availability. And the Gulf Coast in Louisiana, the industrial center there, has a lot of ammonia production, has a lot of steam methane reforming, and so there's a lot of high purity CO2 which could be used to produce algae, and that would happen at a very low carbon intensity. As you can see in these figures, the most favorable algae production location that we found would be Florida, apart from the lack of high purity CO2 available there. So considering the availability of high purity CO2, Louisiana and the Texas Gulf Coast look very good. So that just gives you a flavor of some of the kinds of work that we're doing. There's actually much more going on within our center, but time is limited today. So I want to turn it over to Wee-Sung next, who will spend some more time talking about our work on sustainable aviation fuels.
Thank you, Troy. So yeah, my name is Wee-Sung Lee. I work with Troy at Argonne National Labs Systems Assessment Center. So today, as Troy explained about the the system boundary and what we do here at Argonne, I'd like to specifically focus on the life cycle analysis of the sustainable aviation fuels, which is a very hot topic in this area. So I'd like to give you the brief introduction about this area. Next, please. So greenhouse gas emissions became a very important metric in the aviation sector. So when I try to search flight from, for example, the Chicago from Houston, planning for attending this webinar, for example, then I search it through the Google flights and I search it based on my time availability and the price. And now you may see there's one more section, the GHG emission. Well, please next. So GHG emissions are presented here, in terms of the kilogram of CO2 for each option there. So as you may see there, some options may have less emissions and the higher emissions. So there are many options that we can choose. And in this example, you may see the higher emissions, but there will be also low carbon emission options too. So there are not only about the price or the time. Now the people considers the emission one of the metrics choosing their flights. Next, please. So the aviation demand is expected to keep increasing. So except for the COVID period, near 2020 and 2021, there was a huge drop. But other than that, we expect the aviation demand would increase, both the passenger travel, also the cargo freight. So that means if we don't do anything about the aviation sector, without any mitigation effort, greenhouse gas emissions would be increasing because there's no other option except for emitting more if we just use the conventional fuels and the current technology. So as we see the increase in the demand, we expect that there will be increase in emissions. That's for sure. Next, please.
Wee-Sung, I tried to give you control. See if you can flip your slide.
I don't know whether I can do it.
Okay, I'll stop it and do it again.
Yeah. So I mentioned that we may have more greenhouse gas emissions in the future if we don't do anything. So what else we can do? So the first option that we can consider is the operational improvements, having shorter routes and maybe having more efficient the systems, having fewer travels. That could be one potential option. And the second option would be having the newer aircraft with a higher efficiency. So using better aircraft technology, we may reduce the fuel use for each travel. But what else that we can do other than these two? So in the road sector, maybe we can consider the electrification, like using the electricity with a lower carbon emissions. We can like fuel the cars with electricity, but it's really difficult for the aviation sector to use batteries because of it requires really high dense energy sources. That means liquid fuels. So next, please. So now the aviation sector focuses on the sustainable aviation fuels, which is typically called SAF, and they consider this SAF can reduce the greenhouse gas emissions from the aviation sector significantly. So as you may see from these articles, some airline operators committed that they will reduce emissions by like this amount of emissions by a certain time, and they actually flew with the sustainable aviation fuels from one place to the other. So it's now happening. And then this is really impactful in the aviation sector. So that's why we focus on this area. Next, please. One of the main driver to move those airline operators to make their commitment is actually from the International Civil Aviation Organization, which is ICAO. So in 2016, the ICAO established the CORSIA program. The CORSIA program is a carbon offsetting program. As you may see from the title, it is carbon offsetting and reduction scheme for international aviation. So their commitment, the ICAO's commitment, is that they would like to have the aviation sector emissions will be the carbon neutral growth from 2020, meaning there's no further emission growth from the international aviation. So we may have the same level of the emissions compared to not 2020 because of COVID, they changed it to 2019. So based on the baseline of the 2019 level of emissions, all the airline operators flew international, they need to reduce their emissions to keep the level of 2019. Even though they may have more flights, they need to meet their goals to have this. It's kind of global carbon market to offset. And the main focus is actually, as you may see, the green wedge there, the sustainable aviation fuel will be the key portion for the CORSIA, along with other two relatively smaller contribution from the operational improvements and aircraft technology improvements. So you may see that the CORSIA consider the sustainable aviation fuel as the key factor. Next, please. And also in the United States, we have the SAF grant challenge from the federal agencies like the Department of Energy and Department of Transportation, like FAA and USDA. They launched kind of US SAF grant challenge. So in the screenshot from the DOE's website, they try to achieve a minimum of 50% reduction in life cycle greenhouse gas emissions compared to the conventional fuels, like fossil fuels. And they try to meet a goal supplying sufficient SAF, like sustainable aviation fuels, to meet 100% of the aviation fuel demand by 2050. That means by 2030, they target to have 3 billion gallons per year of the SAF production. And by 2050, they try to reach 35 billion gallons per year. So you may see the very similar figure on the right-hand side compared to the ICAO's the projection. So if we don't do anything, we may end up having the red dotted line because, again, because of the increase in the air flight demand. So, and if we keep the current technology, we may end up having red dotted lines. And by having a better like new aircrafts and having the operational improvements in yellow, and then plus the SAF, then we can get the 50% emission reduction by 2050, or maybe with the more active SAF production, maybe we can even reach to the 100% emission reduction. That requires a lot of SAF. Next, please. So I mentioned the emission reduction, and LCA and would be the part of like the major part for the emission reduction calculation. So you may assume that if I burn like the fossil fuels, or if I burn the biofuels like SAF, emission would be kind of similar from the aircraft. But life cycle analysis consider, I'll explain the details, the difference in the fossil LCA and the SAF LCA, the system boundary. But the biofuels like the SAF can have the emission benefit reduction benefits because we consider the life cycle basis. And the SAF program internationally or federal or state level, they take the LCA as the key like tool to evaluate the emissions and emission reduction through sustainable aviation fuel. Again, the international ICAO's CORSIA will be using the LCA, and at the federal level, US EPA's RFS renewable fuel standard, they use LCA. And other states, California, Oregon, and Washington, at the state level, they also have the program supporting these like the biofuel or SAF activities through the LCA. So life cycle analysis will be the key factor here in analyzing the greenhouse gas emissions and emission reductions compared to the fossil fuels. Next, please. So I will talk about the little more details, how we analyze the emissions of the petroleum fuels and how we analyze the emissions from the sustainable aviation fuels. So LCA, Troy explained the general LCA framework. We have the fuel cycle and the vehicle cycle. But for the aviation sector, we mainly focus on the fuel cycle, meaning for the petroleum fuels, not just about the jet fuel combustion from the aircraft, we also consider the older life cycle stages starting from the crude oil production. So on the far left-hand side, you will see the crude oil will be recovered and transported, and we have the refineries to convert the crude oil into the jet fuel and other fuel types, and we eventually combust it. So from the all stages, we have emissions, and those are all combined together as in terms of the gram of CO2 per megajoule of fuels. And we just not only focus on the emissions from each stage, we also consider, for example, if I use natural gas for petroleum refining, then I also track all the way to the natural gas production and natural gas transmission to the petroleum refining process, so that all the life cycle stages of the input materials will be also covered. So it's a very comprehensive and thorough analysis. And again, everything will be calculated in terms of the gram of CO2 per megajoule, so that the different systems could be compared each other. Next, please. So similarly, when we consider the sustainable aviation fuels, we have the emissions from the fuel use on the far right-hand side. The aviation sector may have the emissions from the combustion. Also, we also considered all the conversion processes. Like this example is a soybean to SAF, like through the hydro processing, which is typically called HEFA processing after oil extraction. But at the very left-hand side, from the beginning, we consider the soybean farming. We start from the farming, and then farming requires the energy and fertilizer, the chemicals. And once we use, for example, nitrogen fertilizer for soybean farming, we also track back how the fertilizer will be produced. And if we use the diesel fuel for farming, then we track back how much energy and emissions will be associated with that amount of the diesel used in the farming. So again, we consider all the life cycle stages to calculate everything in terms of the gram of CO2 per megajoule. Can you click next, please? But the main factor in SAF is the carbon cycle via photosynthesis. So because the carbon in soybean and carbon in soybean derived fuels actually came from the CO2 from the atmosphere. So that like the carbon observed from the atmosphere during the biomass growth could offset the carbon emitted during the fuel combustion, for example, because the carbon comes from the atmosphere. So it's carbon neutral. That's why sustainable aviation fuel typically have relatively lower carbon emissions compared to the fossil fuels. Next, please. So grid provided the carbon intensity values. The carbon intensity is another, like the same word, the life cycle greenhouse gas emissions. So the carbon intensity tend to present it in terms of the gram of CO2 per megajoule. And we, Argonne, participated in the ICAO's fuel task group, where we like developed the carbon intensity values for the CORSIA program. So as you may see on the left-hand side, there are many fuel production options, soft production options from various feedstocks like the agricultural residue or forestry residue with the FT. That's the fuel conversion process. Or we can use a different fuel conversion using different feedstock, like the second one would be tallow or used cooking oil could be converted into SAF using the HEFA process, for example. So Argonne supported the ICAO's CORSIA using Argonne's grid model, and the default LCA values will be available in CORSIA document. And so you may see that the right, at the left-hand side figure, there are like a red dashed line. That's a petroleum jet fuel baseline, which is 89 grams of CO2 per megajoule. So LCA value of the petroleum jet fuel is 89, and other like SAF production, as you may see, some may have very close to zero, like the 7, 8, and some may have a higher, but those are relatively lower than the petroleum jet fuel baseline, meaning the difference between the fossil and the SAF would be considered the emission reduction that could be like major part for the CORSIA program. Next, please. I mentioned about the grid model, and we have the grid, like the very large file with a lot of data sets and with extensive pathway list of the pathways. We recently split the aviation part to give the more interactive, user-friendly interactive interface so that the people can test multiple feedstock and the conversion like pathways, and they can see the results right away. And I can just show you kind of quick overview of this module so that maybe if you're interested in checking the results, you don't need to like understand very details, but you can quickly check the results. Can you click next? So on the left-hand side, you may be able to check, select the feedstock and conversion types and the data sources. Then click next, please. And then the table on the right-hand side shows all the inputs used for this calculation. So you may just use a user-defined values, or if you change the numbers, the results will be updated right away. So interactive module. And in LCA, the co-product handling is very important. And this, we also have this feature here. And on the right-hand side, you will see there are many metrics, environmental metrics, like from the energy use or greenhouse gas emissions, and the results are presented for the upstream and the on-site emissions, and each contribution are is presented on the right-hand side. Can you click next? And on the very far right-hand side, aircraft types also impact the results when we generate the results in terms of the per kilogram kilometer or per passenger kilometer. So based on the aircraft type and then the fuel economy, like the fuel intensity, energy intensity values by aircraft types, we could also generate the results in terms of by like the types of the aircraft types. Next, please. Yeah, next. Can you move to the next, please? So the benefit of having this module is that we can have the very consistent data structure. And again, it's very user-friendly. So whoever who wants to check, they can check the results and they can see the impact of the changing the parameter right away. And the most importantly, we use very reliable data, mainly two sources, GRID and the ICAO CORSIA program. So this module can be mainly used by the stakeholders or by other researchers to verify and to improve their carbon intensity values. So meaning if I have carbon intensity values 50% reduction compared to the fossil, but if I want to reduce further, they can change their parameters to reflect the additional emission reductions. Next, please. So this figure is from the module that I just showed you. It's a very, we just generated the default values from the module again, compared to the baseline petroleum, you see the emission reductions through soft pathways. And this, again, I'd like to emphasize that this is just one snapshot, but each like a pathway can have the variations depending on the actual conditions in the farming or the fuel conversion processes. Next, please. So I mentioned about the carbon intensity values and life cycle greenhouse gas emissions, and the SAF can reduce greenhouse gas emissions compared to fossil. But what do we need to do if we'd like to further reduce the carbon emissions from the aviation sector through SAF? SAF is not the same SAF, like depending on the feedstock and the conversion technologies, it could be different. So typically waste feedstocks generally tend to have lower carbon intensity values compared to other crop-derived sustainable aviation fuels, mainly because they don't have the emission burdens of their upstream, the feedstock production. Also, many people talk about the induced land use change. So when we have the crop type of the sustainable aviation fuels, we may also consider the induced land use change, and the waste feedstock do not have those impacts. So by having less fossil energy inputs, we can reduce the emissions, like using renewable hydrogen, renewable electricity, renewable natural gas, or biomass. We can reduce the carbon intensity values. Also, for example, like municipal solid waste, if it is used for the fuel production, the fossil portion in MSW tend to increase the carbon intensity values. So by avoiding fossil carbon inputs, we can reduce the carbon intensity values. Also, there will be other additional emission credits, like considering the avoided business as usual emissions, but it's like too complicated. So today I'll just skip to next slide. So I mentioned that the previous, the figures are all based on the default very specific condition. So emission reduction can happen even from the same SAF production. So this slide shows that the first bar presents the petroleum jet fuel. The second bar, actually, the corn ethanol that is converted into jet fuel. So by default, that value has like around 72 grams. But by implementing more renewable energy sources, like switching the natural gas to renewable natural gas or using the renewable electricity, we can further reduce the numbers to like 17.3 there. But if we consider even the carbon capture and sequestration from the CO2 from the ethanol production, then we can actually reduce the carbon intensity values to make it negative value. And on the right-hand side, there are many other options that are focusing on the farming activities. So considering the more like active involvement in the farming activities, we can further reduce the greenhouse gas emissions. Next, please. So in summary, SAF can play an important role reducing the greenhouse gas emissions from the aviation sector, which is really difficult to be electrified. And the emission reductions can be quantified through the LCAs. And LCA is not just about the research activity, it's used for the many regulation or the programs. And the LCA can be used to identify emission hotspots, and we can use LCA to further decarbonize the aviation sector. And the Argonne has supported SAF programs through research activities using the green model. Thank you.
Hi, thanks. So I'm Jared Kelly. I'm going to be talking today, shifting gears a little bit, moving away from fuels and into battery space. So I'll be talking about the impacts of battery electric vehicles with a little bit of discussion on implications for grid resilience. Next slide, please. So you've learned a lot about the GREET model. You've seen a lot about what it can do from a fuels perspective, and this extends to other frames as well. So we think broadly about vehicles, right, as having a well to pump emissions. That's the associated with the production of fuels or energy, the pump to wheels. So that's the combustion of fuels within a vehicle. And then we also have to account for things like the vehicle manufacturing stage and the performance of the vehicle. So we use a tool caught Autonomy, which is vehicle simulation tool to understand the size of vehicles, the performance of vehicles, et cetera. And then we also consider the end of life, right? And so basically what I'm showing with the slide is that we have a lot of different tools that we're working with, and it's important for us to leverage those. And so if we go to the next slide, when we drill down on batteries, we have to think of a number of different stages, right? There's the resource itself. So we go through resource to manufacturing, to consumption and use within a vehicle, waste, and then recycling. Next slide, please. So we're doing the resources is what I'll talk about next. Next, please. And to do that, we break the GREET model into two pieces like we had talked about. We have the GREET 1 model, we have the GREET 2 model. The GREET 2 model is focused on these aspects of vehicle production. So this is all of the stages of producing a vehicle. I like to say that the GREET model is, it tells us all of the energy and materials that are associated with producing all of the energy and materials that we use. So we have raw material extraction, we have material processing, we have vehicle component production, we have the vehicle assembly, and then we get to the end of life. So that's disposal, recycling, and those stages there. Next slide, please. So, okay. We're supported by a number of different programs within the Department of Energy, and those help us to understand the various materials that go into vehicles. So, you know, there's all the folks on this call understand there's many different types of materials that go into vehicles. There's many different types of materials that go into batteries. So we capture all the different materials, what they're made, what's associated with producing them. And so that gives us an implication or an idea into the supply chain impacts that are associated with material production. We carry that forward into battery component and battery pack modeling. So that includes things like chemistry, processes, bill of materials, lifetime, and location. That helps us understand the supply chain impacts associated with battery production. We carry that forward into electric vehicle modeling. With that, we have the vehicle characteristics, the usage rates, the cradle to grave. That's what we mean by when we say C to G, that's cradle to grave. Possible second life, possible end of life impacts. And that really gives us a total perspective of electric vehicle use, production, and end of life. Next slide, please. So if we drill down on just one material here, right, we have this kind of effort from most of the materials within the GREET model that we cover, but drilling down onto just the LCA, the inventory sort of analysis that would be associated with production of lithium, we have lithium from a couple of different assets, right? We can think of brine-based lithium, so that would be the sort of lithium that's coming out of South America, or we can have lithium from an ore process, that's spodumene generally, and that's going to be coming out of Australia. So we go from basically material recovery, concentration, transport stages, conversion to lithium chemicals, lithium carbonate, lithium hydroxide, additional transport stages towards cell production. So the battery is comprised of a cell, and then we should actually have a cathode stage here as well. So there should be a cathode production stage prior to cell production. And then we have cell production, transport, and then module production, potentially transport, pack production, potentially transport, et cetera, until it gets into the electric vehicle itself and is used, and so on and so forth. Next slide, please. So the battery electric vehicle contains a battery, right? And that battery is comprised of many different materials. And so this is just showing us what the battery looks like. We can see that, of course, there's an anode current collector, there's a cathode current collector, and those are going to be your copper and aluminum. And then we have the anode itself, which is typically graphite with a binder. Can also be silicon doping, silicon components in there, potentially lithium metal for future considerations. There's a separator, and then there's the cathode material. And the cathode material is what a lot of folks are considering at this point in time, right? That's going to be your LFP, so lithium iron phosphate, your LM, your lithium nickel manganese cobalt, so NMC cathodes, your NCAs. NCAs typically is what Tesla is mostly using in their vehicles, so they are putting in LFP in different vehicles in different parts of the world. So there's a lot of different components that are associated with the battery, and there's a lot of different materials that go into those components. And we cover all of that. We try to be exhaustive as best as possible, and so we consider those here. Next slide, please. So the next stage that we would think about then is manufacturing, so making the battery itself. Next slide. So for that kind of coverage, right, I was talking about what's a battery made of, but there's also, in addition to all these different materials and stages of production, there's the assembly stage. And the assembly stage is energetically intensive because you basically have to have dry room conditions. And that means that it doesn't scale linearly. So the more you produce, the more modules that you can, or battery cells that you can produce in one location, the better. Right. So you've got a big hit. It's basically a big capital expense if you think about it that kind of way. And we carry this through also to stages of recycling and disposal, as we can see here. A couple of different recycling stages considered: pyrometallurgical, hydrometallurgical, and direct. And I'll talk about those a little bit later. But this is showing the comprehensive coverage that this model has. And it's informed by another Argonne model called BATPAC, which is focused on modeling the characteristics of the different batteries. So that's how we inform all of our modeling. It's really informed by the other good models at Argonne, the other information that we can find elsewhere. Next slide, please. There seems to be a fair amount of complications with merging our different slides together. So this is just showing the work that we conducted with SQM, who is a major lithium producer out of Chile. And this was an opportunity for us to get primary data. So the production data associated with the Chilean operations in Sal de Atacama for brine extraction, but we also were able to then work with the folks in SQM to understand basically a modeling effort of spodumene-based production of lithium in Australia and conversion of that in China. That allowed us to look at these various production stages in significant detail, all the way from the brine or ore through the concentration, through the conversion to the lithium chemicals and to cathode powder production, and ultimately into a battery itself. And that has a publication that is shown. Next slide. So when we think about these different batteries, one of the things that I mentioned was we have different cathodes. Cathodes are where a lot of the activity is occurring in trying to change battery density. And obviously energy density is really important because that allows you to basically extend your range for the same weight of material or weight of a battery. So what this is showing is the bill of materials associated with the NMC variants. So those unfamiliar, this is stoichiometric relationships of nickel to manganese to cobalt. Typically we say NMC 111, 532, 622, and the numbers are correlate in XYZ form to the N, the M, and the C respectively. The NMC is one of the dominant chemistries on the market, and so something that is of great interest to folks. And so what we're showing here is essentially that as you maintain a particular energetic capacity, so I believe this is for an 84 kilowatt hour battery, you see the associated weight of that battery broken down by different components, and you can see that it's lighter as you get more energy dense, which makes sense, I think, to probably everyone on the call. Next slide, please. Again, I feel like we're having a lot of trouble with some of the text things here. So my apologies for that, but I can still walk us through this. One of the things that we look at and we're concerned about is supply chains. So what does it look like if you make these different materials or you extract these different materials from different parts of the world? And what we're showing here is a comparison of these different battery chemistries along with where the primary production locations would be occurring for these different materials from a greenhouse gas perspective. You can see that if we just focus on one of the blocks, let's say, so the NMC 811 to the far right, looking at the US, China, Japan, Korea, and Europe, you can see that the US and Europe in particular has the lowest greenhouse gas emissions associated with the production of the battery, followed by the US, and then Korea, Japan, and China, respectively. And that's related to to a large degree on the electricity grids associated with these regions. And so again, as we move from the NMC 111 over to the 811, as you increase energy density, you decrease greenhouse gas emissions associated with the battery generally. And then there's variance in where you produce the batteries themselves. Next slide, please. Now, consumption and use. Next slide. So obviously, Troy and Yusung talked quite a bit about the upstream and the implications of producing fuels in from different pathways. And the same can be said for electricity, right? So this is just an illustration of the sort of, all the background information that we have on the electricity that's going into the grid. Next slide, thanks. So this is just a map of the characteristic emissions rate, greenhouse gas emissions in different parts of the US. And this is for 2019 data. We update all the time. So this is constantly representing better and better information. Next slide, thanks. We can take that information and bring it into an analysis of an electric vehicle versus a gasoline vehicle. To orient you on these slides, what you're seeing in the far left is a gasoline vehicle with a 31 mile per gallon gasoline equivalent against an EV with a 300 mile range that has 124 mile per gallon gasoline equivalent. The bar associated with the EV in the far left is using the US average grid emissions as characteristic associated with those. And you can see there's these different colors. The colors represent the vehicle in the blue, the battery itself in the yellow. In pink, that's the upstream emissions. So that's the emissions associated with producing the energy. So electricity emissions go there. And then we have tailpipe emissions in the darker red, pink, bit colorblind, apologies for that. Now, as we move further to the right, I've characterized things for the electric vehicle by fuel and by region of the US. So looking at coal, natural gas, and renewables, and then different parts of the country, upper Midwest, Texas, California, and the Northeast. This is just showing how these EVs would compare against a gasoline vehicle. These are comparable vehicles as modeled through the autonomy simulation tool. So it should be a pretty apples to apples comparison in terms of the performance parameters. Yeah, so this is showing that the battery itself is a big component of the EV, right? It's a significant burden you can see there, but that still doesn't, to a large degree, offset the benefit from the use phase. Next slide, thanks. This is looking at that in even broader context, both currently and into the future, for a variety of different vehicle types. If we focus on the plot on the right, that's showing the various current and future vehicles for gasoline, diesel, corn ethanol, hybrid vehicle, plug-in hybrid with a 50 mile range, fuel cell vehicle from different types of fuel cell. And then we've got the battery electric 300 mile range, as you can see. It's a little hard to view this one. And so one of the things to just observe in the top portion of that is that we have a variety of different pathways that we're considering for the future for the fuel cell vehicle, for the battery electric vehicle. And so just we can see that as generally we're expecting advancements in vehicles just generally, but we can see significant potential for reductions in associated greenhouse gas emissions with vehicle electrification. fuel cell vehicles, and even hybridization in biofuels can yield significant greenhouse gas reductions as well. Next slide, please. So one of the conversations that I believe is going on in this group, and what I was hoping to address at least a little bit, is, and again, this conversion of slides is problematic. So I'm missing some of the text that would be beneficial. So I'll talk through it. So essentially, the idea that if I'm understanding this group correctly, you're thinking about battery electric vehicles and potential for resilience to the electrical grid. And you can think about that from grid support. But, so there can be, it's important to recognize that charging and discharging batteries degrades them. So you reduce the battery's longevity by just charging and discharging it. But also the longevity of the battery declines with age too. There's calendar aging. So the fact that it exists means that it's going to be having some degradation to it, at least the current instantiations of these batteries. You can reduce these things by staying within certain state of charge windows, by not having extremely high charge discharge rates. So that's one thing to increase the longevity of the battery. But we can think of a few different types of grid support. And this is where, unfortunately, the text is cut. So I'll talk through this. We've got the grid support of passive grid support. So you can think of if your vehicle is connected to the grid and there are some issues associated with grid, that the grid itself could say like, okay, that's an extraneous load and we're not going to charge the vehicle. So that provides a support to the grid that allows it to then provide electricity to critical loads. Let's say hospitals and the like, right? We could also have a certain situation where we have active grid support, where the battery electric vehicle feeds into the grid to help support critical loads at a distance, right? So that could again be that your EVs in your driveway is able to help support grid electricity to critical loads. And then we can also think about how a battery electric vehicle could be in an off-grid situation, supporting a home that's off-grid, that's maybe mostly powered by solar electricity, and there's a situation where they need additional electricity, and the battery within the vehicle can support that. Again, I think it's important to highlight that there's no free lunch here, right? There is an effect on your battery by providing that support. So if you're feeding your electricity into the grid, that has an effect on your battery's longevity. And with the expensive batteries, you might do calculations to identify the value of that. So that's just a food for thought sort of thing. I was thinking that might be something relevant to this group. Next slide, thanks. So there's also, now we get to like the end of life, there's the recycling, but there's also the transportation stage and getting it to recycling. So next slide, thanks. This is an issue. Who's responsible for these batteries at their end of life? Where do they go? Is it going to have a backhaul sort of thing like we see with lead acid batteries? Who's going to be collecting these? Who's going to be moving these along the life cycle, the life chain to get them to recycling? Next slide, please, because this can be an issue. So if you have certain situations where these batteries that look like, is this playing for other folks? You able to play that, Troy? Yeah, thanks. If these batteries are on a conveyor belt, like the small ones, obviously not the kind that go into your Tesla, but a small battery that that's basically the same shape as your battery in your traditional vehicle, that can become a big issue. Seems like it's paused again to me. Yeah. And this can represent an issue to worker safety. And this is a video showing an instance where a lithium-ion battery has gotten onto a conveyor belt with lead acid batteries and yields a pretty dramatic result, as indicated right about here. So there's significant risk associated with these batteries contaminating other battery streams. Nobody was hurt here. We have this courtesy of Richard Leiby from the Association of Battery Recyclers. So this is a concern. It's something that's being addressed. There are a lot of groups that are focusing on this kind of issue. But even simply transporting lithium-ion batteries from one place to another at their end of life is representing a challenge. So there needs to be efforts in that space to ensure that this value chain can be retained, because there is a significant value associated with these batteries at their end of life. Next slide, please. And that brings me to the recycling. Next. So as I was talking about, these batteries are made of cells. Those cells get rolled up essentially into modules. Those modules get brought together in packs. Basically, you don't break things down into at the end of life beyond the module level. Next slide. When the modules are evaluated, they basically there's dismantling, the modules get evaluated, and then they get graded into, let's say, shown here as a gold, blue, and a gray. And that allows them to be routed into potentially a remanufactured battery pack, a second life application. So that might be grid support applications, or they might go to recycling. And being able to understand these stages is really important. So especially now when we think about recycling, next slide, thank you. Recycling represents opportunities. And we have models at Argonne to help us understand that. This is the EverBat model. So it represents a variety of different recycling pathways that are under investigation. There's a resale center here at Argonne that is actively pursuing the different approaches to recycling, in particular direct recycling. So it's cathode recovery and relithiation potential. Next slide, thanks. And the question is, well, what are these different types of recycling and what do they represent? So pyrometallurgical approaches, smelting is basically throwing it into a fire, right? And if you look at this diagram here, it's a rough diagram of the production processes associated with the battery. And you can see if you go to the smelting stage, you basically get all the way back to the ores. So that's in the red there. And so you have to go through all these different stages to get back to a battery. If you go to a hydrometallurgical approach, you get to the yellow. So you have fewer steps to get back to the battery. So you've retained value and energy. And then finally, if you get to the green, that's direct recycling. And that's where you recover the high quality cathode material that can be reutilized. I believe that's my last slide. And I think we can open it up for questions. Thank you.
Thank you. Thank you very much, Troy, Jared, and Yusing. We have a couple of questions, and I think, Troy, you did answer one of them, but just for the sake of interest, we'll just go to the open question, or you did just answer that as well. So I think one basic question that some of the students may have is that how different is the GREET model than existing in built softwares like Gabby or SEMA Pro?
Yeah, can you hear me all right?
Yes.
Okay. Yeah, GREET is its own database and its own software. We have two versions of GREET. One is in Excel, which gives a lot of flexibility for the user to set things up and use them as they want to. The other is GREET.net, which is more of a database application and a little more structured around how you design the models. What we found is our stakeholders find a lot of value in GREET and the data that it contains. I would say of our users, while a number of them are actually doing full LCAs with GREET, there's a whole other category of users who are referring to GREET for the data pieces that they're using for other types of analysis. So I would say, yeah, all of these tools and databases are useful, and GREET has its place amongst them.
Thank you. And one good thing that GREET offers is the access to a free, completely free tool, which softwares may not be giving that. So I think we are running very short on time, but is there any other questions from the team, from the participants? If not, so I have a question, and this is more of a broader scope for the purpose of disaster resilient food, energy, water systems. So Troy, you explained your or the Argonne National Labs work in systems modeling for energy systems, which is at the core, but then you also go into water footprint, and also you mentioned agriculture connections to that. So when disasters strike, especially in the Gulf Coast, all of these systems have a failure. We go into a failure mode, and then we come back, and then that's the resilience. So how do you, and this is an open question to all three of you, how do you think the systems models and understanding the life cycle of these systems can help us in understanding how to respond to disasters better? It's an open question.
Yeah, that's a good question. I think that what I would say to that is we're going through a transition to decarbonize the US economy. And together with that transition is an opportunity to make things more resilient. And participating in this consortium really, I think, gives an opportunity to expand on what we've done. We're doing a lot of analysis looking at, how we can have lower carbon fuels, transportation systems, energy systems, and how we can decarbonize agriculture, how we can reduce, we're looking at other water stress, nutrient impacts. But resilience is an important aspect, and it's something that, should be part of the mix of things that you consider when you're looking at technology transitions. The other side is when there is a disaster, as you mentioned, those systems need to be brought back up or rebuilt. And when there's more extreme damage, that's an opportunity to rebuild things both in a more resilient but also a more sustainable way. So I think the work that we do can contribute to looking at a specific system and how it could be redesigned to be both more resilient and more sustainable.
Thank you. I think we have run out of time, but we still have 63 participants here. So that means that there is been very good interest. If there is one more question that is open, and we'll just take that as the last one. So could you all comment on the ease of talking to industry about some of these modeling developments? Seems like talking to people in relevant industries for your applications are important sometimes. So how would you address that?
I can.
Yeah, do you want to take that, Jared? That would be great.
Yeah, I can at least start. So we engage quite extensively with industry, actually. We get contacted by folks within industry to perform lifecycle analyses for them. They have questions about the work that we do and want better information. And then we do disseminate our information via journal publications, public talks, active engagement with industry partners. I think some of the other folks on here, I am involved with the US Drive. So that's a partnership between the DOE, National Labs, several different automakers, the big three among them, and then a bunch of different energy companies as well. So we have active engagement through those channels with organizations. So it's a good question. Making sure that the work that we do is understood is critical. Troy?
Thank you. Yeah, Troy, go ahead.
Yeah, maybe I can just add to that. I think that because of the reach and impact of GREET, we do have a lot of interest from industry to ensure that what we have in there reflects the best understanding. So that results in industry coming to us when there's something that should be corrected. The other thing is, I would say DOE, our sponsors, have a lot of mechanisms that help us to engage with industry. So when we have large consortium projects like the CoOptima project that I mentioned, or the RECELL, those have industry advisory boards that provide feedback to guide the work. On the other side, DOE runs funding opportunities where we partner with industry. So really the research is benefiting scale up or commercialization of a technology, or developing something that a company has interest in. So that's another way that DOE is ensuring that the work that we do is relevant for industry.
Yeah, and I could add to that from the perspective of Direfuse, we are trying to bring together academic, industry, and governmental, especially federal, state, and local level, to work together for convergence. And that's where the convergence core research perspectives come in. We are engaging with industry at different levels, but mainly focusing on small businesses and local businesses and their understanding of these processes, because that's where a lot of the bottom line for them lies, in the economic bottom line, and not some of the other perspectives. So how can we make information available to them? How can we make these people more conversant and make it part of their learning and decision-making process? So again, for a pitch for Direfuse, we have our in-person workshops. So if you're attending this webinar, we have the opportunity to meet you in person, and we'll have the perspectives from industry and the government taken into account on the same table. So I think this would be a nice point where we can stop today's webinar, but I think the discussion is very important, and we have contacts for Troy on our website as well as here. So if you want to connect with the GREET modeling team in Argonne for any of your needs, you can directly contact them, or you can be part of Direfuse and we can put you in touch. So thank you very much. And thank you, Troy. Thank you, Jared. And thank you, Yusung. This has been really great for us. And I think we'll keep the dialogue on. Thank you so much.
Thanks for the opportunity.
Thank you so much for having us.